Hey, physical science kids, Mr. Tima here. Welcome back. We're going to start our unit on astronomy, one of my favorite things because, I got my little dancing alien dude here. It's almost hypnotic. It's like you can't stop staring at him. All right. But astronomy, one of the big reasons I got into science. So I'm so sick of this cold weather. I wish spring would hurry up and get here. Actually, it doesn't work that way, Paige. The seasons are determined by the Earth's location in its orbit and relative to the tilt and the axis with respect to the sun. Which what you should have said is, I wish we would hurry up and get to spring. Maybe if I walk faster, that'll help. The Earth's already going 67,000 miles per hour. What difference will that make? Hey, wait up. Okay. Stupid cartoon, but really actually good. It's not like we can hurry up. The Earth is doing what it does, and we're already moving really, really fast. And again, you guys know that the Earth's weather determines on how it gets around the sun and everything like that from middle school. So cosmology. Okay, cosmology, not cosmetology. Okay, cosmetology is the study of like makeup and stuff. Cosmology is the study of how did the universe begin, evolve, and what is it made up of. Okay, and it all starts with something called the Big Bang Theory. You guys know what the Big Bang Theory is? Yeah, right there. All right, Raj, Raj and all them. All right, so yes, of course, that is not it. Okay. The Big Bang Theory, okay, of course, is the universe started with a big bang or an explosion and has been expanding ever since. A rapid expansion of space itself. It's not like it was a room. It's not like there's a room and it's expanding to fill the room like gas particles. It literally is not only expanding, but it's making the room bigger. The room itself is expanding. The house is growing to hold all that stuff. And we assume, looking at the oldest light in the galaxy, we can calculate that it happened about 13.7 billion years ago. Okay, some people say, well, how is this? This isn't true. How did this happen? Well, there's evidence. Okay, the fusion of small elements into larger ones, like hydrogen plus hydrogen into helium, like we learned about back in nuclear chemistry, something called cosmic background radiation, and something called redshift and blue shift. Again, if you notice, you don't know what those two things are right now. We're going to cover these later on in the semester. Right now, you just kind of need to know these three things. Like if I asked you to list them, you would need to know them. Okay? So there are two models of what our universe is doing. There's the steady state theory, and the steady state theory is the universe has always existed and always will. And this is really like a positive outlook. This is kind of like a really positive way to look at the universe. Okay. The other way is something called the oscillating model. And the oscillating model means the universe will rapidly expand, then it will slow, and then it will eventually contract on itself, kind of like an accordion where you pull out and you push back in. You pull out and you push back in. So it's like the universe at some point went down into something, and then there's a big bang that's going to get out here and it's going to reach a limit. And then once it reaches that limit, then it's going to start contracting in on itself into something, maybe something called a black hole, which we'll talk about later. And then it keeps going and then it'll start over again. A lot of people tend to think the oscillating model is something that needs to be followed because think of things. Things tend to happen in cycles. Okay. The weather, life and death, things like that happen in cycles. So, galaxy. What is a galaxy? A galaxy is a large group of stars, gas, and dust held together by gravity. There are about 40 billion galaxies that can be seen. That means we have identified 40 billion galaxies. Galaxies are gatherings of ancient matter left over from the Big Bang, which you talked about, or we talked about in the Star Struck article. Most agree at the center of galaxies are extremely massive black holes. Okay, we'll talk about what a black hole is, but you can't see them. So, why do they think that? Well, if there was a star at the center of our galaxy, if there was a huge star, we'd be able to see it. And when we look at galaxies right now, we can't see anything in the center of them. So, the Milky Way galaxy, that's our galaxy. Now, we said there's 40 billion galaxies that we've identified. Well, we're just talking about our galaxy, one of them. Our galaxy, the Milky Way, contains 400 billion stars. 400 billion stars. So 40 billion galaxies, 40 billion galaxies and 400 billion stars. We're talking about 16 trillion stars. And then around each of those stars, there's planets around most of them. So the idea that could there be life around other planets? Absolutely. Our sun orbits the center of the Milky Way. It takes about 225 million years for our solar system, our sun, to go around the Milky Way. We think we've done about 22 orbits since then. So if our galaxy had a birthday, we'd say our galaxy is 22 years old. Okay, kind of like 22 cycles around the center, if you will. All right, so what is the speed of light? Well, the speed of light is how fast light travels, but what does that mean? Well, let's take an example of this. Let's actually look at this for a second. Speed of light is 7.5 orbits in 1 second. That means light can go around the Earth 7.5 times in every second. That's how fast an actual light molecule to scale if it was traveling from the Earth to the moon. It would only take 1.2 seconds to go from the Earth to the moon if we were traveling at the speed of light. Right? So if we were traveling at the speed of light and we were going from the Earth to Mars, it would take 3 minutes and 2 seconds. Right now, traveling at the highest speed that we can travel, we estimate it'll take 70 to 80 years to get to Mars. So, I mean, even though that's not an impressively fast on your screen, you got to think about the impressive amount of distance that it's covering. And like it's typing there, if you were to send a message, it takes about 3 minutes for it to get back. If you ever watched the movie The Martian, it talks about this. Almost 53 minutes to get to Jupiter. Pluto, 5 hours. Nearest star to Earth take you 4 years. Andromeda, next galaxy. There you go. All right, so just something kind of neat to look at there. All right, something to look at just to kind of get your brain working on these distances, okay? So our galaxy, the Milky Way, is roughly 100,000 light years across. That means traveling at the speed of light, it would take us 100,000 Earth years to travel from one end of the Milky Way all the way to the other end of the Milky Way. Okay? Our sun lies about 26,000 light years from the galactic center. So we're about halfway out. Okay? If this was the center and it's 100,000 light years across, so that means 50,000 to the middle. We know about halfway out is where our galaxy is going around, or excuse me, our sun is in our galaxy. Okay? But the weird thing about these galaxies is that even though they're really far across, like 100,000 light years across, they're only about, if we took this and we kind of flipped it on its side, it's kind of like a frisbee. They're only about 1,000 light years thick. Again, an imaginable amount of time. Okay? An imaginable amount of time. But the idea is it would only take you about 1,000 light years or 1,000 years traveling at the speed of light to go from top to bottom, if you will, than it would for you to go across the galaxy. Okay, so kind of think about it traveling like a frisbee. All right, here's another quick look at something, a question. You speed is a relative quantity. So really, how fast are we moving? Literally, how fast are we moving on Earth right now, and so forth and so on. Let's take a look.
How fast are you moving right now? That seems like an easy question. The first tempting answer is, I'm not moving. Upon further reflection, you realize that maybe the Earth's motion counts. So a second tempting answer is 19 miles per second around the sun. But then you recall learning that the sun moves around the center of the Milky Way galaxy. And the Milky Way moves within the local group of galaxies. And the local group moves within the Virgo cluster. And the Virgo cluster moves within. How fast are you moving is not an easy question. When mission control tells astronauts how fast they're going, there is always an assumed standard of rest. At the start of the voyage, speeds are given relative to the launch pad. But later, when the launch pad is just one more arbitrary place down there on Earth's spinning surface, speeds are given relative to the idealized, non-spinning, pinpoint center of Earth. On their way to the moon, Apollo astronauts had a hard time answering the question, how fast are you moving? Speed away from Earth was one thing, and speed toward the moon was quite another. That's because the Earth and the moon move relative to one another. Of course, speed is a relative quantity. When Captain Kirk asks Lieutenant Sulu if the Starship Enterprise has reached a speed of warp 7, Sulu should reply, relative to what, Captain? Such a sassy reply may get subordinate Starfleet officers in trouble, but it is the only good answer to the question, how fast are you moving? This is basic relativity talking. Not fancy Einsteinian relativity, but good old-fashioned and still correct Galilean relativity. Galileo seems to have been the first person to realize that there is no such thing as an absolute speed. Speeds are relative. This means that speeds only have meaning when they are referred to a reference frame. Presumably, that reference frame is itself at rest. But then we have to ask again, at rest relative to what? Because even the concept of rest has lost any hint of absolute meaning. Speed is relative and rest is relative. Earth's speed is 19 miles per second relative to the sun. The Enterprise's speed is warp 7 relative to the center of the Milky Way galaxy. Your speed is 0 relative to your easy chair. But depending on where you sit, it is hundreds of miles per hour relative to Earth's center. When we furrow a brow and ask, but how fast is Earth really moving? We imagine spaceship Earth plowing through the ocean of space as it orbits the sun. But space is not an ocean. It has no substance as water does. Space is not a thing. Space is nothing. Space is no thing. You can move between 2 points in space, say between Earth and Mars, but you can't move through space. There's nothing to move through. It's like trying to say how much a hole weighs. A hole weighs exactly nothing, because a hole is nothing. It's a void, and so is space. To move relative to nothing is meaningless. The concepts of speed and of rest have only relative meaning. They are absolutely meaningless. They mean something only with respect to arbitrarily chosen, artificial frames of reference. If someday you are buckled into your spaceship and you see from the side window, say, a space station whiz by at constant speed, there is no way to know which of you is really moving. Neither of you is really moving because there is no deep reality about constant speed. Constant speed in a straight line has only relative meaning, a kind of relative reality. Does this mean that all motion is relative? No. Some motions have only relative meaning, but some motions have absolute meaning, are absolutely real. For example, constant speed is relative, but change in speed is absolute. Calling something absolute in science means that arbitrary standards are not used in its measurement. It is unambiguously measurable. When your spaceship fires its engines, your change in speed is beyond doubt. You feel it in your stomach, and your ship's sensors can measure it. Outside your window, the passing space station may seem to be changing speed, but the beings inside the station will not feel it, and no sensors can measure it. You are really changing speed, and they really are not. There's something absolutely real about changes in speed. The same goes for rotation. If your spaceship is spinning, you can feel it, and your ship's sensors can measure it. The space station outside may seem to be going around you, but it is you who feels queasy, not the folks in the space station. You are really spinning, and they really are not. There's something absolutely real about rotation. So some motions are relative, and some are not. There is no deep reality about constant speed, but changes in speed are deeply real, and so are rotations. We have to be thoughtful in our analysis of everyday experience in order to identify what is deeply real. Since we can be fooled by perceptions as basic as speed, maybe every perception deserves careful scrutiny. This is what inspired Einstein to his incredible insights about the speed of light and forward time travel. Knowing how to identify what is deeply real is tough and important work. If a police officer ever pulls you over for speeding and asks, "Do you know how fast you were going?" An insightful, though perhaps unwise, reply would be, "Relative to what?" And then, as you sit in the back seat of the police car and feel it accelerate toward jail, you can add, "But some things are absolute."
All right. Well, I know that that took a little bit of a complicated view for some of you, but some of you probably really enjoyed that. And that's what it's all about. But the idea of how fast are you going? Well, it all has to do with what relative you are to everything else. All right. We're almost done here. Well, so think about this: 1 light year is the distance light can travel in 1 Earth year. Light travels at basically 3 times 10 to the 8th meters per second. What are you really looking at? So I have to ask you this question. When you think about light takes time to travel, when you look up at the stars, like if you go outside tonight and you look up at the stars and you see a star up in the sky, let's say that that star is 1 light year from you. Well, if you look at that star, the light you're seeing actually left that star 1 Earth year ago. So, really, anytime you look at the stars, you're looking into the past. Wait, what a minute? Well, think about this. If you were able to see the surface of this star right here and it was 1 light year away, then you're really looking at the star or what it was happening on that star or what the star looked like 1 Earth year ago because it took a year for that light to get to your eye. Another way to think about it is what if it was 100 light years away? Well, then it's really like you're looking 100 light years into the past because that light took 100 years to get here. And here's the really creepy part: a lot of stars that you see in the sky aren't even there. They're hundreds of thousands of light years away, but their light is just getting to Earth. So we see it maybe as a new star, but it's been gone for a long time, but the light is still traveling here, so we still see it. It's crazy. It's crazy, crazy, crazy. And we'll talk about that some more. So there are 3 types of galaxies. There's the barbed spiral galaxy. Okay, this is the most common. This is like ours. And the barbed spiral means there's a center, and then it kind of does this. It kind of has like a pinwheel shape to it. It has these arms that come out, these barbs, if you will. Okay, so a barbed spiral galaxy. Sorry about that. I forgot I got to erase all the time. Okay. There's the elliptical galaxy. Now, the elliptical galaxy is like what I like to call the football shaped galaxy. This is a horrible drawing on the computer, but there you go. Here's my the football shaped galaxy. Some people call it the clam shell. Okay. But if it was a football, we look at it like this. There's the laces up on top. Okay. Sorry, bad drawing, but there you go. All right. So that's the football or the elliptical galaxy. If you know what an ellipse is, okay, we'll do that. And then finally, the other one is called an irregular. So if it's not a barbed spiral and it's not an elliptical, so basically if it's not shaped like a clamshell or a football, or it's not shaped like a pinwheel, then we call it an irregular galaxy. We just say, hey, there's so many other shapes out there. We're just going to call it irregular. A lot of spirals, a lot of ellipticals, but then you have an irregular. Okay. I always thought this one kind of looked like a shrimp. Okay, we'll put our legs down, put our little fin down here. There we go. And then we'll put a little eye here. Okay, there you go. There's my little shrimpy guy. All right. So, all right. So those are your three types of galaxies. One last thing to think that's kind of cool is this is what happens when two galaxies come together. Okay, I know. So Ohio State actually accumulated these pictures some years ago. Now, what's crazy is some people say, well, I thought you said it takes a long time for this to happen. Actually, it does. It takes years and years and years. We're talking about hundreds of thousands of years, millions of years for two galaxies to collide. So, what we have to do is we have to find different stages of them in the galaxy and then we piece them together. So, what happens here? Okay, what happens here is these two galaxies get somewhat close to each other and a new galactic center forms. And they start spinning, but in the middle, this new galactic center forms. And if you notice, they keep spinning towards each other, towards each other, towards each other until they combine into a new, larger galaxy. Okay? And what happens is, people, is the bigger galaxy wins out. So, like, if our galaxy would hit into another galaxy, I mean, our solar system would get ripped apart. Life would probably end. It's kind of a not a nice thing, if you will. All right. So this is the beginning of the Notes Astronomy on galaxies. Hopefully, you enjoyed some of those videos, and we'll talk to you soon. Until next time, Mr. Tima out.